This is Unit 5, Lesson 3, Lines of Symmetry. And we are going to be talking about the different lines of symmetry and different polygons and figuring out how many there are and the different transformations that we can do on them. So let's start off with defining what is a line of symmetry. Well, the line of symmetry is a line separating a figure into two halves that are mirror images. So when I think of line of symmetry, the thing that comes to my head is a heart. That's not the type of shape we're going to be talking about, but you know, if you were to fold a piece of paper in half and cut this shape right there, when we unfold the paper, the whole heart would show up. So that's kind of like the line of symmetry on that heart shape. We are going to be looking at the line of symmetry in regular polygons. And that's our second and last term that we're going to look at. Regular polygons are two-dimensional figures, and in a regular polygon, all sides and angles are congruent. Squares have 4 equal sides, 4 equal angles, and they also have 4 lines of symmetry. And that's kind of what we're going to see in any shape that has all congruent sides and all congruent angles. If we had an equilateral triangle where all the sides are the same length, they're congruent, all the angles are congruent, we would have 3. A triangle is a 3-sided figure, so it has 3 different lines of symmetry. If we had a octagon, a regular octagon that has 8 sides and 8 angles, then it would also have 8 lines of symmetry. So let's draw our square. Point A, B, C, and D. And then we can draw 4 different lines of symmetry in here. So let's draw a line of symmetry that goes down the middle. Another line of symmetry that goes across the middle. Then we have a line of symmetry through this diagonal, and a line of symmetry through the other diagonal. Those are all the 4 places where we could fold this square in half and it would overlap. Now, what if I took this square and I just twisted it that way? I twisted it 90 degrees. Well, if I twist it 90 degrees, then side A is going to move over here. So where I had B, that's now going to become A prime. Here's where A was in the pre-image. We twist it and A ends up over here in the image. So it was originally B, but now it's A prime. Side B started right here. When we twist it 90 degrees, it ends up here as B prime. Originally that was C. C began right here, and then it twisted 90 degrees to come right here, where we originally had D. When we twist D 90 degrees, it comes up where we started out with A. So what we just did is a 90-degree rotation. Now this axis of symmetry that was going through the center, when we twisted it 90 degrees, it became the axis of symmetry going up and down. When we took this line of symmetry that was going up and down and twisted it 90 degrees, it came right here. So it looks the exact same. If I hadn't labeled the sides or the angles, the corners, I wouldn't know that I had rotated this at all. Now what if we take this original one and we rotate it 180 degrees? So we're starting here and we're going to twist it all the way around. My arm doesn't bend quite that way. So when A begins here and it twists 180 degrees around, it comes over to this corner. B starts out here. When we twist it 180 degrees around, it comes to this corner. C starts out right here where A has now ended up. We twist it 180 degrees around, and it goes up here to where A started. D would have started right here. When we twist it 180 degrees, it ends up over here. The axis of symmetry started right here, 180 degrees around, it ends right there. So it's almost like it's just going backwards, but it's going through the same place. This vertical axis of symmetry may have started here, 180 degrees around, it's now going up. And we don't really think of the axis of symmetry as going up or down. The point is that it hasn't really moved, it's still in the same place. So here's our original. This is what happens to a square with a 90-degree rotation, and this is what happens to a square with a 180-degree rotation. Now let's take a look at rectangles. So rectangles aren't regular polygons because all of the sides aren't the same length. And all the angles are congruent, but not all the sides. So it's not a regular polygon, but it still can be rotated. So I'm going to start out with my original that has A, B, C, and D. And if I were to fold this rectangle in half, I could fold it in half and have it perfectly overlap right down the middle, going up and down, or right down the middle, going side to side. So here is our original. Let's copy that original down again. And let's take that original and we're going to rotate it 90 degrees. So if I take this rectangle and I rotate it 90 degrees, it's going to go right here. It's going to be going up and down instead of side to side. We still have an axis of symmetry. We have two of them still. A started right here, and when it rotated 90 degrees, it came over to here. B, starting out right here, rotated 90 degrees, came down to the bottom right. C started in the bottom right. We rotate it 90 degrees, it goes to the bottom left. D started out in the bottom left. When we rotate it 90 degrees, it's going to go up to the top left. That is a 90-degree rotation of a rectangle. Now what about a 180-degree rotation of a rectangle. So we start out with A, B, C, and D. Well, when we rotate 180 degrees, A goes from here all the way around 180 degrees to here. B goes from the top right around 180 degrees to the bottom left. C goes from the bottom right around 180 degrees to the top left. And D goes from the bottom left 180 degrees around to the top right. So you can see we kind of did a diagonal shift, just like what happened up here with the square. That was my 180 degree rotation of a rectangle. Now let's look at a 180 degree, or not 180 degree, let's look at rotations of trapezoids. So a trapezoid is a four-sided figure where two sides are parallel and two sides are not parallel. I'm going to look at an isosceles trapezoid. And in an isosceles trapezoid, we have a pair of parallel lines and then our other pair of lines are congruent. So it looks something like this. I've got two parallel lines that are not the same length, and then I have these two not parallel lines that are. We'll call this A, B, C, and D. Think about taking this trapezoid and folding it in half. There is only one place where I could fold it in half, and it would be symmetrical. And that only place is right here. If I folded it right here, we would have this point sticking up and that point sticking up. So the only way I could rotate this is if I were to rotate it all the way around a full 180 degrees. What I can do is I can reflect it over this line of symmetry. So we're basically going to just swivel it over its own line of symmetry. A started out here, but now it's going to end up over here. B started right here, but when I flip it and do that little swivel, it ends up over here. C started right here, but after the flip, it ends up over here. And D started out over on the right side, but after the flip, it ends up over here on the left side. We still have our axis of symmetry going down the center. And I just realized I said 180 degree. This is a 360 degree rotation to get it to end on itself. So we can only do this flip thing with an isosceles trapezoid. If I had a non-isosceles trapezoid like this one, where we have parallel lines and then not congruent lines, I can't fold it in half. If I were to fold it in half right there, we would have this big long piece sticking out. The only way we can transform this and end up with something symmetrical is if we do, once again, a full 360 degree rotation. that would give us a reflection on itself. This last shape we're going to look at is a parallelogram. And parallelograms have two pairs of parallel sides. A square is technically a parallelogram, so is a rectangle. So we're going to say our parallelograms don't look like squares or rectangles, meaning that the parallelograms we look at are not going to have angles of 90 degrees. A parallelogram without an angle of 90 degrees has no line of symmetry. That means we have no possible rotations. The only thing we can do is flip a parallelogram. So here's my parallelogram, ABCD. And the only thing I can do is flip it horizontally. So let's say we had an imaginary line of symmetry out here. If I were to flip it across that line, it would end up over here. We would have B prime, A prime, D prime, and C prime. C came from here to here, B from here to here, A here to here, and D here to here. So that would be a horizontal flip. I could also do a vertical flip. Vertical flip would take it over that imaginary line I just drew in, where we have D prime, C prime, B prime, and A prime. Or my other possibility would be to do a 180-degree rotation. So we could twist this around 180 degrees to the point where we have a shape that looks kind of like this. C rotated 180 degrees to here. B rotated 180 degrees down to here. A went 180 degrees over to this corner, and D went 180 degrees to right here. So we've got a 180-degree rotation, a horizontal flip, and a vertical flip. So it's important for us to understand how we can manipulate these different shapes and how we can manipulate them around our axis of symmetry. Before we finish this up, I just want to emphasize finding the axis of symmetry for different shapes. So let's say I have this hexagon. I want to find every axis of symmetry. So if I were to fold it in half right here, that would work. I could fold it in half here. I could fold it in half right here. I could also fold it in half through the sides rather than going through the corners. And here through the sides, and here through the sides. So that gave me 1, 2, 3, 4, 5, 6 different axes of symmetry. Let's look at an equilateral triangle where all the sides are the same length. I could fold it here, 1, 2, 3 different times. You might say, hey, we could fold it right here as well. But if you folded it in half there, this part would come up and this part would come up. So it would end up looking like this with the tip of our triangle hidden underneath. That doesn't really work out. So remember, an axis of symmetry splits something into two equal halves. And we can rotate around and reflect around an axis of symmetry.